couple of other important things to know for the exam is if you have a capacitor, which again is the two parallel plates that we've been talking about, and of course there's a charge placed on each plate, and that's when the capacitor is all charged up, so to speak. And the relationship between the value of the capacitance in farads and the voltage and the charge in coulombs is the equation we've used quite a bit. Q equals C times V. I remember it as Chula Vista. That reminds me that the Q is by itself and the C and the V are multiplied together. And the capacitance, of course, then you could say is Q divided by V, just manipulating that same equation. And then we came up with, for a parallel plate capacitor, that capacitance is also equal to epsilon 0 A divided by D, where D is the spacing between the plates. A is the area of the plates. And those are all in SI units of meters or meters squared. And then epsilon 0, of course, is the permittivity of free space that we've talked about quite a bit. And if you have a dielectric, the way you can think about a dielectric is you have your two plates, and you have some material in between the plates. And if you think about the fact that the material is an insulator, that means the electrons can't move freely. So dielectric is an insulator. And the molecules within the dielectric will align themselves by being induced or by experiencing the electrical fields from the plates, and they'll align themselves somewhat so that you have the negative side on the side that's closer to the positive plate, and the positive side on the side that's closer to the negative plate. And all the molecules in the dielectric will do that. And the extent to which they do that defines the strength of the dielectric, or the dielectric constant, which has this symbol K. It's kind of like a scripted K, like that. But that's the dielectric constant, which tells you how much that dielectric is going to do that polarization of its, well, semi-polarization, at least the alignment of its molecules with the surrounding plates like this. And the more it does it, the greater the K. The greater the K, the greater the capacitance. So the equation for the capacitance, if you take that into account, becomes epsilon 0 A times K divided by D, where again D is the spacing and A is the area. We talked about RC circuits, so if you have a capacitor and a resistor, and they're in a circuit like that, which is of course the same as a circuit like this. These are electrically identical. And if the capacitor has an initial charge across it, or an initial voltage, that charge is going to drain through the resistor, and the voltage across the capacitor is going to equal the initial voltage across the capacitor, which is usually the battery voltage that was used to charge up the capacitor, which from lab, if you remember, looked something like that. Actually, the switch was over here. The switch was right here. Let's see if I can fix that. I just erased everything. I think I will erase everything just so you can see it again. So redraw the whole thing. Here's the capacitor. Here's the switch. Here's the resistor. And the switch switches between the battery and the resistor, if you like. It's not as clean as it could be drawn, but it's the basic idea that the switch is either connected to the battery, in which case the capacitor charges up, and then when the switch is switched down, the capacitor is charged up. I'll get rid of the battery in that case, and it's tied to the resistor now. The issue being that the capacitor now has an initial voltage across it, which is the battery voltage, which is this. And then it was the e to the minus t over RC. So that was the equation for that. And so being able to manipulate that and knowing that when V of t is equal to 37% of V0, at that time, t is equal to RC. That's the RC time constant. And that's why that 37% is often used. So, going back to the capacitor, one more thing I want to say. In between the plates of the capacitor, there is a potential. So the potential, let's say this is the negative plate, and this one here is the positive plate. The potential goes from 0 to V. And you could figure out what the potential is at any point in here. The potential at any distance between these two plates is going to be equal to the electric field times the distance from the negative plate. So when you get all the way to the positive plate, your potential will then be the full potential, V0, between them. But anywhere in between these, it builds up linearly until you get to the top. And this is the linear equation that tells you what the potential is between the two plates at any point between the two plates of the capacitor. This is true for a uniform electric field, which is true when you have a parallel plate capacitor. And the lines of equipotential look like this, if you remember. And the electric field lines will go from the negative to the positive, and the lines of equipotential are always perpendicular to the electric field lines. One other thing I'll mention in this review video is if you put capacitors in parallel, the equivalent capacitance is the sum of them. When capacitors are in series, on the other hand, the equivalent capacitance for the series case is 1 over C1 plus 1 over C2. Now, you could do this. This is certainly possible where you have two capacitors in series, let's say, and they are in parallel with a single capacitor. Or you could have it other ways too. You could have, just like we did with resistors, but use the same thinking. These two in series, you find an equivalent capacitance for those using this equation. Let's call this one C1, this one C2, this one C3. And this is V. And so you could rewrite the circuit like this. And these two are in parallel. So then you just add them. So you take the value that you found here and add it to the value you found there, and that would give you the equivalent capacitance. All right. Another thing, you remember that, of course, in parallel, voltages are the same for across capacitors. In series, capacitance circuits, I should say, charges are the things that are the same, even if the value of the capacitances aren't. Okay, so, and then that combined with Q is equal to C times V can give you whatever you're looking for, whether it's a charge across capacitor, the voltage across the capacitor, if you know the capacitance and the charge. So if you know any two of them, you can find the third. So we didn't do so many cases where you'd combine series parallel capacitance but you can. Same rules apply. That's enough for this video.